Hello everyone. Today we will solve some numerical problems on partially filled waveguide. So, to start with, this is our first numerical problem and it states that consider the dominant mode of the partially filled guide for B greater than A as shown below. Okay. Denote the empty guide propagation constant d equals to 0 by B naught equals to given root under of k2 square minus pi by b square, and show from the Taylor expansion of the transcendental equation about d equals to 0 and kz equals to beta naught that for small d kz is beta naught plus epsilon 2 upon epsilon 1 k1 square minus k2 square upon 2 beta naught times d upon A. Okay. So, we will start solving this problem. So, at first in the given question there is one partially filled guide. Okay. So, this is y axis x and this is the partially filled guide. Okay. So, this is the origin, in this direction we have z and this is A, this point is D, and let us have this as epsilon 2 comma mu 2 and this as epsilon 1 comma mu 1. Okay. So, this portion is epsilon 1 comma mu 1 and the upper one is epsilon 2 comma mu 2. Okay. So, in this question it is also asked that we need to consider for small d. Okay. So, it is given that the empty guide propagation constant is given by, so the empty guide propagation constant that is if d is 0. Okay. So, if d is 0, then the empty guide propagation constant is given by beta naught equals to root under k2 square minus pi upon b whole square. Okay. And we need to show that for small d kz is given by b naught plus epsilon 2 upon epsilon 1 k1 square minus k2 square upon 2 beta naught d upon A. Okay. So, in the given figure the waveguide is dielectric filled between x equals to 0 and x equals to d. Okay. Or it can be considered that it has two dielectrics. Okay. So, the waveguide is dielectric filled between 0 to d, it is filled with epsilon 1 mu 1, and from d to A it is filled with epsilon 2 mu 2. Okay. So, therefore, we can write like this, that the problem, therefore, the problem contains therefore, the problem contains two homogeneous regions. That is from 0 to d when x is ranging from 0 to d, and the other one when x is ranging from d to a. Okay. Now, such problems can be solved by finding solutions in each of the regions such that the tangential components of E and H are continuous across the common boundary. Okay. So, therefore, satisfying the boundary conditions at the conducting walls, we can write down satisfying the boundary conditions So, satisfying the boundary conditions at the conducting walls. We can find out the potential function psi as, so for the first one for is psi 1, so it can be written down as C1 cos of k x1 x sin n pi y upon b e to the power minus j k z z. Okay. This is the first one, and the second one is psi 2 is C2 cos of k x2 a minus x sin of n pi y by b e to the power minus j k z z. So, this is the first one and this is the second one. Okay. With n equals to 1, 2, 3 and so on. Now, it has been anticipated that ky is equal to n pi by b and kz must be the same in each region for matching the tangential E and H at x equals to d. Okay. So, the separation parameter equations in the two regions we can write down like this. The separation parameter equations in the two regions can be written down as k x1 square plus n pi by b square, since ky is n pi by b. So, k x square plus k y square plus k z square equals to k square we know. So, hence we can write k x1 square plus, in place of ky we will write n pi by b square plus k z square, that is equals to k1 square, and this can be written as k1 square is omega square epsilon 1 mu 1. Similarly, k x2 square plus n pi by b square plus k z square equals to k2 square, that is equals to omega square epsilon 2 mu 2. So, we can denote these two equations as number 3 and equation number 4. Now, then we can find out the fields. Okay, and after finding out the fields and imposing the boundary conditions and the matching at the boundary, we can write k x 1 upon epsilon 1 tan of k x 1 d equals to minus of k x 2 upon epsilon 2 tan of k x 2 a minus d. Okay. So, let us denote this as equation number 5. Now, both k x 1 and k x 2 are functions of k z, okay, and this equation we can call it as a transcendental equation for determining all the possible k z's, that is the mode propagation constant. Okay. So, equation 5 can be written down as, this one can be written down as transcendental equation, and this is used for determining all the possible k z values, okay, where k z is the mode propagation constant. Now, when d is small, the approximation, okay. So, when d is small, let us suppose when d is small, then the above equation can be approximated as k x 1 square d upon epsilon 1 is approximately equal to minus of k x 2 square a minus d upon epsilon 2. Okay. So, this is the case when d is small. So, let us denote this equation as equation number 6. Now, what we will do, we will write this equation by denoting it as a function of k z and d. So, we can tell f of k z comma d is equal to k x 1 square d upon epsilon 1 plus k x 2 square a minus d upon epsilon 2 is equal to 0. Okay. Therefore, from equation number from equation number 3 we can write k x 1 square is equal to k 1 square minus pi by b square minus of k z square. Okay. Also, in the given question, it is given that b naught square is equal to k 2 square minus pi by b square, where this b naught is known as, we can name it as empty guide propagation constant. And the condition is for d equals to 0. Okay. So, from this, when b naught square is equal to k 2 square minus pi by b square, we can write this pi by b as pi by b square, we can write it down as k 2 square minus b naught square. Okay. Therefore, we can write k kx1 square is equal to k1 square. In place of pi by b, we will write k2 square minus in place of pi by b whole square, we will write k2 square minus b naught square. Okay. So, kx1 square is now k1 square. In place of pi by b whole square, we are writing k2 square minus beta naught square. So, it will be k1 square minus k2 square plus beta naught square minus kz square. Let us give this as equation number 7. Similarly, from equation number 4, we can write kx square in terms of beta naught square. Okay. So, therefore, we can also write in a similar manner that from equation number 4, we will have kx2 square is equal to k2 square minus pi upon b square minus kz square. Okay. So, in place of pi by b, we will substitute pi by b square, we will substitute k2 square minus b naught square. Okay. So, k2 square minus of, so pi by b in like k2 square plus b naught square minus kz square. We substituted in place of pi by b square, we substituted k2 square minus beta naught square. Okay. So, now k2 square will cancel out and we will be left with kx2 square as beta naught square minus kz square. So, this is equation number 8. Now, what we will do? We will substitute this kx1 square value and kx2 square value in place of f of kz comma t. So, now f of kz comma d, we can write it was f of kz comma d was kx1 square d upon epsilon 1 plus k it will be k x1 square d upon epsilon 1 plus k x2 square a minus d upon epsilon 2. So, now we will substitute the values that we obtained for kx1 and kx2 in this equation. So, we will get in place of kx1, we will substitute equation number 7. So, in place of kx1, we will write k1 square minus k2 square plus b naught square minus kz square. Okay. And this is d upon epsilon 1 plus kx2. In place of kx2 square, we will substitute beta naught square minus kz square that we obtained from equation number 8. Okay. So, now we will write in place of kx2 square beta naught square minus kz square a minus d upon epsilon 2. So, now simplifying this, we can write it like d upon epsilon 1, this is beta naught square plus k1 square minus k2 square minus kz square plus this will be a minus d upon epsilon 2 beta naught square minus kz square. So, let us denote this equation as equation number 9. Okay. Now, what we will do, for the Taylor expansion, we will write down the Taylor expansion in the neighborhood of x y equals to x comma y equals to a comma b. Okay. So, the Taylor expansion can be written, okay, for like in the can be written like f of x comma y is approximated as f of a comma b plus f x a comma b x minus a plus f y a comma b y minus b. So, here we have neglected the second order and all the higher terms. Okay. So, now in this general formula we will place, and then we will have k z comma d, f of k z comma d can be written like f of b naught comma 0 plus f of z b naught comma 0 k z minus beta naught plus f of d beta naught comma 0 d. Okay. So, this is equation number 10. Here we have neglected. So, we can write like this, neglecting second order and higher terms. Okay. So, now we will write, so first we will find out f of beta naught comma 0, then we will find out f of z beta naught comma 0 and then f of f d beta naught comma 0. Okay. So, from equation number 9 we can see, okay, we can see f of beta naught comma 0. Okay. So, equation 9 we had, okay. So, here we will substitute in place of k z we will substitute beta naught and in place of d we will substitute 0. Okay. So, while substituting d as 0, the first term is becoming 0, okay, and when we will substitute we will substitute beta naught in place of k z. So, again the second term is also becoming 0. So, basically from 9 we can write f of beta naught comma 0 is 0. Okay. So, this is equation number 11. Now, we will find out f d beta naught comma 0. Okay. So, for this we need to find out first f of d. So, f of d is del f del d. So, we will substitute the equation number 9 with respect to d. So, we will be getting on differentiating with respect to d, from equation 9 we will get from the first term we will have 1 upon epsilon 1, because we are differentiating with respect to d. Okay. So, from the first term we will get 1 upon epsilon 1 beta naught square plus k 1 square minus k 2 square minus k z square. Okay. and from second term we will get plus this will be beta naught square minus kz square and minus 1 upon epsilon 2. So, this is f of d, that is del f del d. Now, we need to find f of d for beta naught comma 0. So, now f d beta naught comma 0. So, again we will place in kz and beta naught in this, it gets cancelled out, okay. And here also, so we will get one upon epsilon 1 k1 square minus k2 square. Okay. So, this is equation number 12. Now, we will find f of z beta naught comma 0. Okay. So, for this we will have f z is del of f del of kz. Okay. So, this is equal to, so again differentiating equation number 9 with respect to kz. So, we will get minus of d upon epsilon 1 to kz minus of 2 kz a minus d upon epsilon 2. Okay. Therefore, f of z for beta naught comma 0, again substituting, we will get minus 2 because kz is 0. So, the first one will be 0. So, we will left out with minus of 2 beta naught, d is 0. So, a upon epsilon 2. So, let us give this as equation 13. Okay. Now, we will substitute all these values, that is equation number 11, 12 and 13 in equation number 10. Okay. So, substituting 11, 12 and 13 in 10. We will get f of kz comma d, the first term was 0 plus kz minus beta naught, the multiplied term kz minus beta naught minus 2 beta naught a upon epsilon 2 plus 1 upon epsilon 1 k1 square minus k2 square multiplied by d. Okay. So, therefore, we can write f of kz comma d as k1 square minus k2 square d upon epsilon 1 plus here we will have 1 upon epsilon 2 minus of 2 beta naught a kz minus beta naught. Therefore, so we can write this as k1 square minus k2 square d upon epsilon 1 equals to 2 beta naught upon epsilon 2 kz minus beta naught times a. Okay. So, kz minus beta naught is coming as k1 square minus k2 square d upon epsilon 1 multiplied 1 upon a epsilon 2 upon 2 beta naught. Okay. From here we will get kz as we will get beta naught plus epsilon 2 upon epsilon 1 k1 square minus k2 square upon 2 beta naught d by a. Okay, so thank you. On next class we will again solve some few more problems on partially filled guides. Thank you.